So just a very brief introduction to the topic. This has been a wonderful 15 years for me as a press officer because I can always count on there being a press conference on exoplanets. But I should also just inject a personal note. It's also been a sort of a bittersweet 15 years because getting near the end of my official career as an astronomer, I kind of wish I were starting over again. I worked most of my career on binary stars, and this is sort of a natural extension of it. At any rate, we are going to be talking about exoplanets from the exhilarating to the exasperating this time. All of our speakers are from the Center for Astrophysics, which is not surprising, is it? Of course. It being a hub of activity for this. We'd like to, at the outset, thank David Aguilar and Christine Pulliam for organizing this. Ofer Cohn will be our first speaker, talking about magnetospheric structure and atmospheric joule heating of habitable planets orbiting M-dwarf stars. The long title conceals some very poignant and simple, straightforward messages, which I think you will find very interesting. Then Kepler 56, Present and Future Configuration and Stability by Gongjia Li. Then three distinct exoplanet regimes inferred from host star metallicities by Lars Buchhava, and then the Kepler 10 planetary system revisited by HARPS North by Dimitar Sasolov. All the panelists will speak one after another, and then we will get to the questions afterwards. So please hold both your applause and your questions to the question and answer period at the end. If you're attending online, you can send your questions via the chat room, and I think that's about it. We can get started. Ofer?
Thank you very much. So, how do I start my presentation?
Reset button. Yeah. And then you should see.
Oh, reset. Okay. Thank you. Yeah. Okay. Hello, everybody. It's nice to see all of you. Yeah, it's on. So I'm going to talk about essentially the space environment of close-in planets orbiting M-dwarfs. And let's start by just briefly discussing M-dwarfs. These are the most common stars in the universe, and they're about 1/10 to 1/2 the solar size, the sun in mass and size. And they are also very much cooler and fainter than our own sun. And M-dwarfs were at the center of the discussion in the context of exoplanets, in particular in the context of habitability. And planet habitability was defined essentially whether we can find liquid water on the surface of a planet, and that of course depends on the temperature that we have on that planet, and that temperature depends on the light that is coming to the top of the atmosphere of a particular planet, and that depends on the distance from the star and the light of the star, whether it's brighter or fainter, and if the planet is further out or closer in. And in the particular case of M-dwarfs, it should be closer. And we can define the range of distances from the star for a given star, that we call it the habitable zone, at which planet can exist and have this liquid water on the surface. And you can see here on the right, this is the sun or sun-like star, and you can see that the habitable zone extends from about 0.8 astronomical unit to about 2. And as we go to fainter stars like orange dwarfs and finally red dwarfs, you can see that habitable zone get closer in. And in the case of red dwarf, the habitable zone is very close to the star, so close that, in a matter of fact, it's easier for us to detect planets, and in particular terrestrial planets like the Earth. So the excitement about red dwarfs in the context of planet habitability was that it is most likely to find terrestrial planets in the habitable zone around M-dwarf stars. However, we can we know from the sun and from other stars that there's a continuous emission of particles or flow of particles from the star into the interplanetary space, and this is the solar or stellar wind that occupies the volume between the sun and the planets, and the planets reside in this flow of particles. Now, in the case of the Earth is far away from the sun, and it is shielded by a magnetic field that we can see here in this cartoon that shields us from this flow. However, if planets do not have strong magnetic fields, they don't have this protection, and over time this flow has a stripping force that can rip the atmosphere from the planet, and we believe that this is partially what happens to Mars in its the process of its the loss of its atmosphere, where over time, here on the right, you can see this flow of particles of the solar wind strip the planetary atmosphere from Mars. So the question is, if we consider planets orbiting red dwarfs in the habitable zone, which is very close to the star, what are the space conditions, and whether or not they are extreme, and therefore they can strip the atmospheres of this planet. So we performed a numerical study, or we used computer simulation to do two things. The first thing we did is we obtained the stellar wind conditions of a known typical M dwarfs, EVLAC, and we calculated the space conditions, or the stellar wind conditions, at the location of the three orbits of three planetary candidates observed by Kepler, and they were published last year in a paper by Dressing and Charbonnet as habitable planets in the or terrestrial planets orbiting red dwarfs in the habitable zone. So you can see here the three orbits of the planets shown in as blue circles, the stars in the middle, and this is the equatorial plane, and it's colored with the values of the stripping force normalized to that near the Earth. And you can see that the stripping force is between 50 to 1,000 times stronger. So these planets reside in a very extreme space environment, and the question is, can they survive and sustain an atmosphere? So the next thing we did, we used a different computer model to calculate the effect on the planetary atmosphere and the magnetosphere, the magnetic confinement around the planet, where here we assume that the planet has an Earth-like magnetic field. And here on the right, I show two cases along the orbit. This is the same planet, and it's the variation of the shape of the magnetosphere, or the magnetic field of this planet, along the orbit. And you can see on the right that there's this red shade that represent the shock, the formation of a shock in front of the planet. And in this case, the planet has a magnetosphere shape similar to that of the Earth, and there's a pretty good shielding from the stellar wind, or the stripping force by the stellar wind. However, we find that most of the time, the planet has the shape shown here on the left, where there is no shielding, or the shielding is very poor, and therefore the planet is much more exposed to the stripping force of the stellar wind, and most likely not to have an atmosphere, or to sustain an atmosphere for a long time. So our conclusion is that even though M dwarfs, or planet around M dwarfs, can be found in the habitable zone, and they can be identified as Earth-like planet, we need to investigate more whether they can sustain an atmosphere, which has a strong impact on their ability to sustain life. And I will move on to the next speaker, Gonji Lee. We will talk about planets around evolving stars.
Thank you, Alfred. It's my pleasure to be here today to share with you the news on the death of 2 exoplanets. And here is my talk. Wait a second, it's going to load. Okay. This is very exciting because this is the first time that we observe an exoplanetary system where 2 of its planets are sentenced to death. And we have calculated their execution time and find one of them is going to die in about 130 million years, and the other one is going to die in about 155 million years. So you may think that these timescales are very long. However, in terms of astrophysical timescales, these are very short, and we are very fortunate to observe a system where 2 of its planets are going to die. So specifically, how will a planet die? So if the star this planet is orbiting around is get aged, the size of star will become bigger And when the size of star reaches beyond the orbit of the planet will be eaten by the star and will be dead, like this. So now we see the planet disappeared. This is very natural, and this will happen to our own solar system in about 5 billion years. At that time, our sun will be aged, and the size of our sun will become bigger to eat the inner planets, Mercury and Venus. Our Earth will not be pleasant for life either, because at that time, the sun will become much brighter, and it will become so hot on Earth that all the water will be evaporated, and our ocean will be gone, and our Earth will be dried up. So now let's get back to the exoplanetary system, where the 2 planets are going to die. The planets are called Kepler-56b and Kepler-56c, where the Kepler-56b is very similar to a Neptune, and Kepler-56c is very similar to a Saturn. They are orbiting around a star called Kepler-56, which is only slightly more massive than our sun. However, since it's aged, its size is about 4 times as big as our sun. It also has another planet orbiting around the star. It's called Kepler-56d, and that planet is more massive than Jupiter. To understand the distances between the planets and the star, we can compare this system to our own solar system, as shown here. So we can see that the inner 2 planets are very close to the star, and the distance between the inner 2 planets is closer to the star is closer than the distance between Mercury to our sun. And the outermost planet is very far away from the star, and the distance from the outermost planet to that star is similar to the distance between asteroid belt to our sun. So as we mentioned, that the death of the planet is due to the aging of a star. So how will a star age? This diagram shows the aging of the star, where stars spend most of their time burning hydrogen on this colorful line called the main sequence. And when the hydrogen in the core of the star gets exhausted, the core will shrink, and the star will burn hydrogen on the outer shell inside the star, and this will cause the star to become bigger and become redder and move to the upper right corner in this diagram to become a red giant. So currently, our sun is burning hydrogen on this main sequence, and Kepler-56 is on its way to become a red giant. So as we mentioned, that the size of the star will become bigger as the star is aging. So we can plot the size of star as the star ages, and we will see that the size of star is increasing. We can quantitatively calculate this number, and from the current age of the star to the time when the planet is eaten by the star, which is marked by the red line here. And we do see that the size of a star is increasing. So what will happen to the orbit of the planet? The tidal interaction is a very important factor here. And similar to the tides on Earth, where the tides on Earth are affected due to the stretching of the Earth by the sun and the moon, for Kepler-56, the star and the planet also squeeze each other and cause tides. And this tidal effect is stronger when the size of the star is bigger and when the distance between the planet and the star is closer. And this will cause the planet to fall closer to the star, as shown here. So here we plot the distance between the planet and the star as the star ages. So we can see that the distance drops due to the tidal interaction. So we can overplot on this figure the size of the star to see the time when the size of the star is the same as the distance between the planet to the star. That marks the time when the planet is eaten by the star. So this way we can calculate the time when the planet is going to die. And we can find the innermost planet is going to die in about 130 million years. And we can do the same for the second planet and find the second planet is going to die in about 155 million years. So here's the animation of our story. So as the star gets aged, its size will become bigger and eat the first planet in about 130 million years. And then the size will become bigger again and eat the second planet in about 155 million years. So again, we are very lucky that we found the first planetary system where 2 of its planets are going to die very soon. And looking at this system is like foreseeing what will happen to our own solar system. So that's all of my news. And next, Lars Bouquet will tell us about planets that are more habitable for life. And let's switch our topics from death to life.
Thank you very much. So the title of the study I'm going to be talking to you about is 3 regimes of exoplanets inferred from host star metallicities. Before I get into the results, let me just remind you of a couple of things. First of all, let's see, is it playing? Yeah, metallicity. We astronomers have a term called metallicity. We have a sort of a peculiar periodic table. We have hydrogen and helium, and then everything heavier than that we call metals. Also, when I talk about metallicity today, we assume that the metallicity of the host star reflects the metallicity of the initial protoplanetary disk of which the planets formed. And just a reminder of what we have in our own solar system. We have the terrestrial-sized planets. These are approximately to scale here on this slide. So we have the solar system planets, Mercury, Venus, Earth, and Mars, all below or equal to 1 Earth radii. Then we have the larger ice and gas giants, Jupiter, Saturn, Neptune, and Uranus, which are all approximately larger than 4 Earth radii. In between there, we don't have any planets at all in our own solar system. But we know that Kepler has discovered an abundance of these exoplanets. In fact, if you look here, here's the size of, here's Earth, and here's Neptune. And in between, we have a large number of planets here. In fact, 75% of the planets discovered by Kepler are less than 4 Earth radii in size. So we really want to know about these planets. Are they rocky planets with a thin, compact atmosphere like the Earth? Or are they rocky cores with some sort of extended hydrogen-helium envelope where there is really no surface and we can't imagine life, like we have it on Earth at least, on them? We also know that metal-rich stars, stars with a high metallicity, seem to, or predominantly, host these hot Jupiter exoplanets. This is well known, has been established for quite a while. But more recently, we and other groups have shown that for smaller planets, here we have down here, there seems to be a wide range of metallicities where these planets form. But we wanted to take this a step further. So what we did was we analyzed over 400 host stars orbited by about 600 exoplanets from Kepler exoplanet candidates, I should say. And here are the results of this study. Down here, we have the metallicities of the host star. So 0 here is around solar metallicity. This is more metal-rich, and down here is more metal-poor. This is the radii of the planets. So here's Jupiter around 11 Earth radii. Here's Neptune, and the Earth, of course, at 1 Earth radius. So we wanted to see if we could figure out if these host stars differed significantly from each other when we looked at their, the planets of different sizes. So we separated the sample into 2 bins, and we asked, are the host stars significantly different? And we did this. We separated the planets at different radii, and the results of that is shown up here. This is the 2-sided Kolmogorov-Smirnov test, and here's the so-called p-value. So what you need to know is, as you go to lower here in the diagram, we have a more significant difference between the host stars. So we find that around here at 3.9 Earth radii, there's a significant difference between the host stars. And we sort of infer that that means, and that's basically this hot Jupiter exoplanet correlation. So these planets over here we assume to be ice and gas giants, which have formed further out and probably migrated in and usually become these solitary hot Jupiter planets. Then there's the rest of the planets, the smaller ones, which are down here. And to our surprise, we found another feature here in this diagram at around 1.7 Earth radii with a high significance. And we really wanted to interpret this, and the way we interpret it is that we think that this is where the terrestrial planets and the gas planets, this is the boundary between the two. So in other words, the planets in this category here are rocky planets with a thin atmosphere, whereas these we call gas dwarfs. So they're rocky planets, but they have amassed a hydrogen-helium envelope before the gas dissipated in the system, but they're not as large and massive as the ice and gas giants, which form further out. We also seem to see that there's really a metallicity sweet spot for these terrestrial planets to form. At high metallicities, again, you tend to form these hot Jupiters predominantly. If you go to very, very low metallicities, much lower than here, at some point, of course, you run out of material to build the planets of, so you can't build any planets. And so there seems to be a metallicity sweet spot, which seems to be pretty much around solar. Although I want to say that the metallicities here, as you can see, have a wide range again. So it's only when you look at a large statistical sample you can talk about the metallicities and how they affect planet formation. We can't just pick one out. There's many, many other factors, of course, than metallicity affecting planet formation. So the last thing we wanted to do was see if there was any dependence on orbital period of this transition, because there's some theoretical work that points that out. Of course, there's other theoretical work saying the exact opposite. But so we wanted to test this observationally. So we looked for this transition at 1.7 Earth radii, but we segregated the sample into 4 bins of period. So down here we have short period planets and longer, meaning that they're farther and farther away from the star. And we look for this transition here at 1.7 Earth radii. That's what we're plotting in this diagram. And lo and behold, it seems that these planets, although there's large uncertainties on these points, that the transition from rocky to gaseous planets seems to increase with orbital period. In other words, this would predict that there should be massive rocky planets at larger orbital radii. And by the way, these planets not made easily theoretically, and I think the next speaker will comment on that. So the conclusions, to wrap up, we see these 3 regimes of exoplanets just from the host star metallicities. And the reason we do this is that it's very difficult to get these dynamical masses of these planets. It's a very hard work. It takes a lot of observing time. So this is a different avenue to sort of ask the same question. We also see the transition from rocky to gaseous planets from these host star metallicities. And this goes very well in hand with some of the recent studies that have shown from dynamical masses that around 1.5 Earth radii, there seems to be a transition from rocky to gaseous planets, which is very close to what we see here. And then we observationally predict these large and massive, heavy, rocky planets without a hydrogen-helium envelope at longer orbital periods. And that leads me to introduce the next speaker, Dimitar Saselov, who will tell us exactly about one of these massive rocky planets that we predict in the study.
Good afternoon, and it's a great pleasure on behalf of the HARPS North spectrograph team to bring to you some exciting news about a planetary system, Kepler-10c. And the news is that we have managed to measure the mass of its second planet, and it turns out to be a very, very massive solid planet. The proper way to call it is something bigger than a super-Earth, so how about mega-Earth? Kepler-10, the planetary system, Kepler-10, is a familiar old favorite of our Kepler team. 4 years ago, it was the one that was our first confirmed rocky planet, and that was the inner of the 2 known planets in that system, Kepler-10b, which is about 1.5 Earth size, about 3.5 Earth mass, lava super-Earth. And the reason it's lava super-Earth, its period is 20 hours, less than a day. So it's very close to its star, and its star is not one of those diminutive M-dwarfs Ofer was talking about here. But it really is more or less a solar analog, a star which is like the sun. So Kepler-10b is very hot, but it is a true rocky planet in composition, internally at least, similar to what we know about Earth. It is a true super-Earth because 3.5 masses is a lot of mass. It has about the same density as the Earth, more dense because of compression, of course. Now, from the very beginning, we knew that there was a second planet there. And we know for sure there are at least 2 planets because both of them are transiting. You know that the Kepler mission works that way, uses transits to detect the planets, so we get the period after a few of those periodic dimics recorded. And we also get the size of the planet, but that's about it. So Kepler-10c, we knew the size from the very beginning. We managed to validate it early on. We knew it was a planet. But with the size of 2.3 Earth sizes, the evidence was increasingly pointing in the direction of this being something of a gas giant, not a rocky super-Earth. And the reason for that is because Kepler continued to discover interesting systems. In fact, the next one in line, Kepler-11, has a planet which has almost exactly the same size, 2.5 Earth sizes. Kepler-11f is its designation. But instead, it has only 2 Earth masses worth of material. So most of its radius is not due to rock and iron and even volatiles like water and ammonia, but hydrogen and helium. Remember about the metallicity from the previous presentation. Hydrogen and helium are different kind of thing. They really cannot be compressed very much, and they make the planet a different kind of planet. So the normal thing would be to expect that Kepler-10c, the 2.3 Earth-sized planet, will be something of that sort and difficult to measure its mass, because if it has a mass of 2 Earth masses in a period of 45 days orbiting a faint star like Kepler-10, it will be difficult to measure it. So it took an effort to measure the mass, but now that we have it, the surprise is it's about 17, actually more than 17 Earth masses. And that brings the density to about 7.5 grams per cc, which is a lot more than what we know of rock here on Earth. But remember, this is a very massive planet, which means those same minerals are highly compressed. So what you see in the density is mostly due to compression rather than different composition. So the composition comes out as being a combination of rocks and some volatiles, probably 5 to 10, 15% at most of water, which under these high pressures would be incorporated either within the matrix of the rock, or even if it's not, then it will be in a solid state. So the proper way to refer to a planet like that is not simply a mega-Earth, but a solid planet. Mind you, it's nothing like an Earth twin. Earth here designate the same meaning as we use for super-Earths, a planet which is made of solids as opposed to a gas planet. And so the question is, how did we manage to measure its mass? And that's actually the most important part of this story, that we are now able to measure the masses of long-period planets around faint stars to very, very high precision and accuracy, meaning that we actually believe our measurements. And the result of that is a big effort by the HARPS North Consortium, which involves the Geneva Observatory as well as the Center for Astrophysics and St. Andrews in Scotland and the Italian National Telescope, and which only started working recently. It's on the Canary Islands, and this kind of instruments are very sophisticated and expensive. We don't even let people like this individual touch it anymore because that's very bad for the precision. But also, you have to understand that instruments don't measure masses by themselves. They're measured by very talented, brilliant, usually young people who go and observe there, as our lead author, Xavier Demusque, who is sitting right here on the first, Xavier, first row, managed to accomplish this amazing feat of measuring the parameters of this planet to such high precision that we can, I can come up here and tell you that we really believe this measurement and it makes a big difference, and it is indeed a surprise. Why is it important? First of all, it is important because a 2.3 Earth size, which is the currency for the Kepler mission, the size, that means that we are digging into a lot more of that gold mine of very many planets that Kepler is telling us are there around stars in our galaxy. So there are more of those out there. We just have to confirm them. We probably found them. Kepler found them as candidates. We just need to confirm them. And it tells us where this transition or this boundary between what we call solid planets and gas planets occurs in terms of mass and radius as well. Why do we care about that? Well, we care about that because it is solid planets that is the place, as far as we know, and we know very little about origins of life, but that's where we think the chemistry is capable of building those molecules which lead to the emergence of life from geochemistry. But while this is great, and it's good that we have good news for more such planets, I'm a theorist, and I have to tell you, we don't know how to make this kind of planets yet. A mega-Earth is a lot of solids concentrated in the same place without any gas. And that is a problem because our understanding of how planets form requires the solids to get together in an environment in which almost 99% of the mass is not in the solids, is in this bluish stuff, which is the hydrogen and helium in the protoplanetary disk. So while you want to be able to combine the solids, and there are plenty of solids, although in the solar system you can see there is not that much solids if you reconstitute it, but that's not the problem. The problem is there is the material, typically, to form a mega-Earth. It's just if you form it in the slow process in which it usually takes to put all this together, you start accreting this blue stuff, the hydrogen and helium, and then you have Neptune, which is at the same mass, but twice the radius on the mass radius diagram. And that's not the whole problem with Kepler-10c. The other problem, or opportunity if you think about life, is that we know the age of the star, and hence we know the age of the planets. The age of the star is almost as old as the age of our Milky Way galaxy, which is fascinating and on its own. But it's also a very interesting point, is that we thought that old stars don't have enough of that solid material yet to form many rocky planets, and hence habitable rocky planets around those older stars will be scarce. Well, probably we are wrong about that, and we should care about that, because when we are thinking about searching for habitable planets, we shouldn't discount the very old stars. And being older myself, I want to finish this on a personal note. More than a decade ago, when our Kepler proposal had been accepted by NASA, I'm a theorist, and I was struggling with this issue of the kind of planets which are missing in our solar system, which we now call super-Earths. At the time, somewhat carelessly, we called them super-Earths. We didn't really think at the time that anybody will use the word afterwards. But basically, at the time, the idea was 10 Earth masses is a kind of good round number, and it makes sense theoretically about this accretion of hydrogen and helium. And the radius that corresponds to that is about 1.7 to 2 Earth radii. So the evidence until this year, and as you heard from Lars, was this was working out great, except now for Kepler-10c, which is confirming the hint about the period dependence that Lars just talked to you. So what I want to say is that I'm more than happy to accept that I was wrong about this, and the new evidence is great. And I have to tell you, I was wrong on two counts. I was also wrong on the count that old stars could not have many rocky planets, which has consequences about the Fermi paradox, and why isn't there so much more life in the galaxy that, we should be worrying about why they're not here yet. I still think that's fine, but I just wanted to tell you it's exciting time to work on exoplanets, and there will be an even more exciting time when we start searching for life around them. Thank you.
We thank all our speakers, and we now open the floor to questions. Please wait for the microphone and wait to be recognized, and Inga has a microphone. And please identify yourself and your affiliation and who you're asking the question of.
Hi. Is it on?
Yes. It's on.
Oh, okay. All right. Hi. All right. I'm just going to go with it. Hi. I'm Miriam Kramer. I'm a writer with Space.com. And I have two quick questions for Gonji. So I'm wondering, first of all, I'm sorry if I missed this during your presentation, but about how far in light years is the system from Earth?
So this system is Kepler 56, and it is about 2,800 light years away from us, and it's in the constellation of Cygnus.
Okay, great.
Thank you.
And then also one other one. If just let's say that someone could observe the eating of these two planets, what could you potentially learn from it? I mean, what could you see?
So for this gaseous giant, or these bigger planets, so possibly the envelope of this giant will be burned off, and then possibly the core of the planets will be left behind, so we will see this dead corpse floating around in the universe. And actually this has already been observed, and there might be candidates of this dead corpse orbiting around the star that's past this red giant phase. Yeah, thank you.
I have a couple questions for Ofer. I'm Todd Henry. We're recons, and we do the sort of survey of the solar neighborhood, and of course most of those stars are red dwarfs, and I might want to come to their defense a little bit. I don't think it's so bad. You mentioned that you chose EV-LAC as the one that you modeled. Why that one?
Mostly because that's a star that actually had data to drive the model with. And I pick him out of 5 options, which this was the star with the most similar temperature and parameters to the stars of the KOIs, the Kepler objects of interest.
So EV-LAC has quite a sordid history. It's one of the most extraordinary red dwarfs there is, with one of the highest activity levels ever measured. As a matter of fact, it might be in the top few. So 95% of red dwarfs or more are much calmer and much less problematic.
That is true, but I would argue that the main point of or the main effect that leads to this strong stripping of the atmosphere is not the stellar activity, is actually just the fact that these planets are very close to the star, so just the density goes up. If you put these planets around the sun in such a distance, the effect might be the same. So it's only the distance that counts. Not only, but mostly.
One, Radcliffe, a couple of quick questions. One for Dimitar is, are we too far past the super-Earth momentum to call this lava-like planet a super-Venus? Because that's what it sounds like. And then a quick question for Ofer. You talked about this difference in the magnetic field orientations and how one creates a buffer and the other one doesn't. Could you inform me about what the difference in that magnetic field is? Was it orientation or something else? Okay.
So the change in the shape of the magnetosphere and the magnetic field orientation is a result of the different location along the orbit where the stellar parameters change dramatically. And we find that at some points along the orbit, the planet has an Earth-like magnetosphere, and at these times it is quite protected. But most of the time, the conditions are such that the shape of the magnetosphere is much less protective for the atmosphere.
I didn't hear the beginning of your question, so could you repeat it, please?
Are we too far past the momentum of super-Earths? I mean that pun intentionally. And can we not call this planet a super-Venus?
Well, actually, again, on a historical point, we used to call things at the time, during 15 years ago, super-Venuses as well, but it had to do with the spectroscopy signatures. I don't think we should make too much of the actual name, except to point out here, or what we could call them, to point out here that there is a significant difference between what we would call solid planets and non-solid planets, meaning having gas, hydrogen and helium, both for our searches for emergence and evidence for life, but also for planet formation. Planet formation, really, there is a difference between whether there are solids, water included, and gas. And so in that sense, what is more important here is that distinction, solids versus gas. So we could simply say, well, super-Earths are just a whole range of possible planets which go to 20, maybe even 30 Earth masses. On the other hand, if there is a period separation that Lars was just pointing out. Maybe we should be more careful in saying this poster child for them, and there is now another one coming up maybe, and what we expect to see at longer periods. They may constitute a slightly different population from the super Earths that we got used to at very much shorter periods.
Hi, I'm Irene Klotz with Discovery Channel and Reuters. For Dr. Saslov, I was wondering if you could maybe just go through a little bit about how a large solid planet would keep on forming and not accrete hydrogen and helium, if that's like a function of time, and then why a planet like Earth would stop. Did it just, like, why wouldn't Earth just keep getting bigger and sort of tap into the availability of hydrogen and helium?
That's a good question, and we need about an hour for a lecture on planet formation. The most important thing for you to know, and for all of you to know, is that this is a very active field, and we don't know the answer. In other words, we have many people with different answers, but there is no consensus on that. The general idea is that you have a disk, which we actually see those protoplanetary disks, with a ratio of 99% gas and 1 to mostly 2% solids. And in that disk, you start forming embryos. We actually call them embryos, small planets, first with the size of Moon and then Mars. And they essentially collect all the solids, eat their feeding zone, as we call them, in the disk at different radii. However, they also interact with each other gravitationally, and sometimes their orbits cross. So they tend to have giant impacts. One of those created probably the Moon in our own planet Earth and the Moon. A Mars-sized body hit the proto-Earth, and that probably happens often. The problem, however, is if you want to form a mega-Earth like Kepler-10c by simply colliding 3 times Kepler-10b's together, it doesn't seem to work. The process is not efficient as you become bigger and bigger. A lot of the mass from that collision gets scattered around. And so the only good way to do that we know of is to simply keep doing it with smaller portions. That is, to feed the embryo in a more regular way throughout the disk. But then you run into this problem, is that the escape velocity at the surface of that growing solid planet becomes comparable to what you would have for the hydrogen and helium gas there. So it starts sticking. The gas is no longer just passing through, but starts sticking. And that, being 99% of the mass, goes into a runaway process, which very quickly makes you into a Neptune and even bigger. So that's the problem, and we haven't resolved it yet.
Thanks. I also had a quick follow-up question for Lars. I hope it's not another sign that I didn't take astrophysics in school. But is the study biased at all because the Kepler is looking at sun-like stars as far as the sizing and basically all the relationships that you're sort of charting between size and radius and so forth with the metal contents of the stars?
Yeah, so that's a very important question, I think, because it is biased. The Kepler mission is inherently biased towards short-period, close-in planets. They're much easier to detect with Kepler. And I didn't have enough time to go into this, but also when we talk about the hot Jupiter metallicity correlation, at that point, when that was discovered very early on, actually, I think it was in 97, that people started talking about that. It was always planets and high metallicity, not hot Jupiter exoplanets. But now we know that it's mostly hot Jupiter exoplanets that form at these high metallicities. So we always have to think of what sample we're looking at. And in this case, we're looking at things that are very common, these 1 to 4 Earth radii planets, but we are inherently biased towards short-period exoplanets. So those are much easier to detect with Kepler. And also, we mostly look with Kepler at sun-like stars. We've chosen to look at those.
Do we have some other questions from the audience? One back there.
Hi, Jeff Founce, Space Review. For Dr. Cohen, how would we actually try and, be able to observationally determine if, in fact, the atmospheres of planets closely orbiting M-dwarfs are being stripped by solar wind? Can you study the stars? If you're able to, or is there some other signal that you were able to detect to be able to determine if these atmospheres are being stripped or not?
Well, one thing we should look for is the magnetic field of the planets. Unfortunately, theoretically, we're not sure whether these planets should or should not have a strong magnetic field to protect them. One thing that people have looked at is what we call star-planet interaction that produce or may produce some signal of a planetary magnetic field. The other thing that people are looking forward to be able to do in a better quality is atmospheric signals or observations of the atmospheres of these planets, and that should help us to indicate also the some properties of the general properties of the atmosphere.
We had a question far in the back, and then I think Rick may have had some questions from the web.
Bill Waller, the Galactic Inquirer. This is for both Lars and Dimitar. This has to do with the metallicity and the sweet spot, and in particular, the favoring of high metallicity for the gas giants. Is there a common explanation for that favoring, for that bias?
Yeah, so there's a general understanding, I guess, that Dimitar was talking about. It's not completely resolved, but one of the ideas is that if you have a high metallicity, you can grow cores that are needed to accrete gas very quickly, and you can grow them big enough that you actually start accreting the gas onto them before the gas dissipates in the system, before the star comes to life and dissipates all the gas. So that's one of the possible reasons for hot Jupiters. But there are other ideas, many other ideas.
So it would begin with a very large rocky core, correct?
Yes.
Any questions from the audience? And as long as we're back there, any questions from the web?
Yes, we have one question from Daniel Fischer, a freelancer in Germany. This is for Ofer Cohen, and it's kind of a follow-up to what you were talking about just a moment ago. Your stripping modeling assumes a magnetic field like Earth's. I think you just said that we don't have a lot of data on magnetic fields of Earth-like planets, but he's wondering if there are any theoretical arguments, for example, why M-dwarf planets might or might not have strong enough fields to better protect their atmospheres.
So actually the problem is that we have arguments for and against stronger or weaker fields in rocky planets around M-dwarf. So it's not clear whether the field should be expected to be stronger or weaker. So in our model we have the ability to tweak this parameter, and we do work on a further study to try different values for the magnetic field to see how strong it should be to well protect the atmosphere in any case.
Okay, and I have my own follow-up on the same topic. If you've talked about stripping of the atmosphere. If you have formed a planet that, for example, also has an ocean, and you strip away the atmosphere, will you lose the ocean too, or is it possible that we could have some planets out there that have lost their atmospheres but still have water on the surfaces?
I believe that there's a good chance to lose the water on the surface, but it's probably a better question for people who do planet formations. You want to comment on that?
No, except that it will be a process in which you will be stripping the atmosphere. The ocean will probably be trying to replenish that. At some point, of course, it will not be able to. So depending on how much water you have, the process may stall or may continue until all the water is gone. It depends on the mass and all the parameters involved.
Are there no other questions? I have a question for Dimitar. Would you say a few words about how you determine the age of these systems, and is there any interaction between the planetary formation and the and your age determinations, where the formation of planets could influence or alter what you think is the age of a planet of a system?
Good question. I didn't dwell on it, but the answer to the last part is no. The age of the planets is determined as a consequence of determining the age of the star, So the assumption is that the planets and the planetary system is of the same age as the star. The age of the star in this particular case was determined in a way which is independent, which is using what we call astroseismology, the fact that stars similar to the sun have acoustic oscillations or waves observed on the surface, which can be studied in a very similar way and techniques which are familiar to us here on the Earth, seismology, which gives you a sense of what is the internal structure of the star. And the internal structure of the star carries information about its age through our very good knowledge of nuclear physics, because you can literally see the amount of helium that has been transformed from hydrogen due to the thermonuclear burning. And this is essentially how we determine the age of those stars. Kepler has revolutionized this area of stellar physics by measuring the ages and doing astroseismology for a very large number of stars. And Kepler 10c happens to be one of those stars. We can't do it for all of the Kepler stars, but Kepler 10c is one of those, and that's how we know that the age is about somewhere between 10 and 11 billion years. So it has nothing to do with what we measure about the planet and what we infer about its formation.
There's a question in the back there.
Hi, my name is David Slisky. I'm somewhat biased as I work with Dimitar as a scientist, but maybe more on the humanistic side of a question. At the end, you alluded to the fact that things that you thought you were certain about a decade ago are now things which, in today's press conference, you deem are false, planets around old stars. In light of Bicep 2's kind of questioning earlier this morning, how do you feel about, are there things that you feel certain about now which you think may be questioned in the future, which will change our perception of life? Or other things, maybe my favorite question to ask Dimitar, what do you think is going to happen in the future? But more from the humanistic side of things.
We have to talk after this, David. That's a tough question. No, thank you. Thank you for asking this, because I think there are two different things. Bicep 2 is an actual measurement, which is a very careful measurement, and it claims what it sees. The theoretical work on super-Earth 15 years ago was a shot in the dark. Nobody had detected a single one until 2005. And we didn't even know if they existed or could form. And so the theoretical work was just a preparation for what Kepler was supposed to see later on, and trying to kind of guide us in where we were going. So that's why the choice was at 10 Earth masses, by the way, because it was a good round number. I think we went into that with our eyes open, and we knew that it will probably change. Except that for the last year, it seemed that it was going right that way. And the part which was escaping me is that it was going in that towards 10 simply because we were doing statistics of a biased sample of planets which had very short periods, which is what happens with all of our planet searches. And now that we are finally starting to reach out into the longer periods, I hope we are seeing a different population and eventually a very interesting population of planets. Am I certain of it? No, I'm not certain of it. The only thing I'm certain about, and I wanted to emphasize in this press conference, is the measurement which was done by Xavier and the HARPS North team, which, just like the Bicep 2 measurement, is an exquisite piece of work. The theoretical interpretation is just to give us a sense of what its implications are.
Any further questions? If not, we can adjourn, and if you have any follow-up questions, you may ask them directly to the participants. I should remind you that our next press conference is tomorrow morning, 10:15 Eastern Daylight Time. What is happening to the sunspot cycle? Stay tuned. Thank you very much.